Okay. So let's start. It is my pleasure to introduce Frédéric Bour, who is going to talk about the world library.
Hi, so yeah, the world library is about having fun making graphical applications in OCaml. First I will explain what exactly is the problem I am trying to solve. There are many ways to render graphics, but I only care about a few specific cases. Then I will explain how to model that in OCaml, what the API looks like when you try to actually implement graphics, and how it is executed on the GPU. The key points of this library are, first, we try to expose the declarative model of vector graphics. If you look at the graphics module from the OCaml distribution, it's an imperative interface. Like it assumes you have a buffer and you apply a few operations on it to change the actual content. Here we want to have a tree, like some way to describe what an image looks like, and at some point send it to the GPU for actual rendering. And this will be done with OpenGL. More specifically, it's OpenGL ES2. It's a very versatile version. It's very portable. It's on all embedded devices, all modern desktops, and even gaming consoles. And third, it's independent from a windowing system. So the library will only turn a high-level description of an image into something visual, but it won't help you getting a surface to render this to. So you will have to interface it with other low-level libraries like SDL, GLFW, or a web browser. OpenGL ES2 is also the version used by WebGL, so you can render into a web browser. I didn't write the bindings for that yet, but it's a small amount of work. There are some trade-offs I made in designing this library. So I care about user interfaces. So my goal are to have a high output quality. In practice, it means good anti-aliasing. If you use the hardware features for anti-aliasing, it will not look as good because it's tailored for 3D rendering. So we have another implementation of anti-aliasing. We care about performance. We want to have a fluid interface. And third point is simplicity. We don't have many resources, so we want to keep things simple. To implement all these goals, we had to give up some expressivity. In particular, clipping is not is quite limited. Like you cannot do arbitrary intersection of images, but for a user interface, generally you have a well-defined goal, and you can a priori design the user interface with these constraints. This wouldn't work for, say, a PDF reader or some graphic applications where the user might input arbitrary or even degenerate geometries. So assuming you control the geometry you are going to submit to the renderer, it should work well with the high quality. Now the model. The basic idea is to design shapes which are subset of the plane. You have a few algebraic constructors which represent some of the cases, and the idea of a shape can be interpreted as a function from a point of the plane to a boolean, which tells whether this point is inside or outside the shape. And if to the shapes you add a paint, so paints are infinite images. It's a point from it's a function from a point on the plane to colors, and colors are 4 values in the unit interval. So interval, it's for the red components, the blue components, the green components, and finally for transparency. So if you intersect shapes with paint, you start being able to express interesting graphics. And that's what we call images. So the interpretation of images is a function from point to colors, but they are more structured than simple infinite images. So you could interpret this roughly like that. Then you can apply transformation. So rather than just directly asking what is the point of an image, you can apply an arbitrary function which will transform the point to something else. And if you repeat this process with many images, you start being able to express interesting graphics. So in this case, we design a few primitive images and we blend all of them with a function which takes the different images and return a composition of the image. Now the API to express this. The few interesting ingredients to express this is first, you will define path. Paths are functions from the unit interval to points, they are continuous, and that's the basic thing we will use to describe a shape. So this is the API which lets you express a path. This is the only imperative part, but the amount of effects is very limited, so it looks like this when you use it. First you move to some origin point, then you draw a line, and you can draw smooth lines. Finally you can close the shape, and that's all. It is imperative for performance reason. The closures that you pass here should not do any effects. The only thing it should do is invoke this context function, and the graphic renderer will invoke this closure at the right time when all resources are ready for rendering. Besides that, the rest of the system is exposed pure interface. Now shapes. Once you have described a path with the previous API, there are two ways to turn it into a shape. The first one is to fill. So you will consider the inside of the path as a shape. And the other way is to stroke it. So you give some thickness to points that are on the path, and this turns it into a surface. So the API looks like this when you apply that to the previous path. And there are a third way to define primitive shapes, and it's a bit more complex. Because not everything is possible to express with this simple API, we allow the user to submit a bitmap, which will be an approximation of an arbitrarily complex shape. The API lets you define this dynamically. And finally, because this is very useful for typesetting text, we have an abstraction to talk about layout. There are many ways to do layout, like left to right, right to left, but there is also line breaking considerations and many more complications, and that's not the purpose of this library. So we expose two low-level interfaces, one to pick fonts and one to select how to lay out glyphs. There is an easy implementation that comes out of the box with not many functionalities. But yeah, with these three ingredients, filling, stroking, and submitting external shapes, we are able to build all the other things we care about for user interface. Now we can give color to these things. So you already saw the uniform color paint. You have a linear one, so it's a simple linear gradient which is interpolated between 2 points. You can do box gradients, so here we add the roundedness of the corners as a feature and the fuzziness of the border. The same with the radial one, so rather than interpolating in a box, you interpolate in a circle. And finally, you can also submit arbitrary pix maps. So same as with the Glyphes Masks, it's a big array of pixels that you submit to the API. You lose the resolution independence property of vector graphics, but in exchange you can express arbitrarily complex stuff or display pictures, which is often useful in user interfaces. Now the transformations. So basically we support all affine transformations, which are transformations that maps parallel lines to other parallel lines. The common ones are translation, rotation, rescaling, and slightly odd one is skewing. So by composing all these transformations, you will be able to make interesting shapes. And finally, you can compose all the images. So in the 4 previous steps, we were able to define a few images, and now we want to compose them. So the first composition is the paint one, which I didn't expose, but which is used in the previous slides. So it's the one that takes a primitive shape and intersects it with an infinite paint. Then we have superposition. So we pick 2 primitive images and we render the superposition of the 2 images. Scissoring. So one of the trade-offs we made is not support arbitrary clipping. The only kind of clipping that we support is intersection with a rectangle. Alpha composition, so you can make one of the image transparent and blend it on top of another one. And now let's look at the execution model. So to describe the smiley that is on the right, we build a tree which roughly looks like this. So the root node will superpose a few different images. First, we want to paint a big circle in yellow and a few other features in black. So we have 2 small circles and smile. Actually, because we're in a functional language, we name every part and we can do sharing. So the actual representation will probably can be made to look like this. There is only a single circle to be allocated and a single smile. To execute this, we will allocate some memory on the GPU. And first for the circle, so let's assume that this step will transform the circle, which is the path, arbitrary complex path that you describe with Bezier curve and so on, into a list of straight lines, like polygons that the GPU can consume. Same for the smile. You will turn it into a lower level representation. And then the renderer will traverse the tree. So in the first step, we allocate memory for all the complex geometry. And then we will interpret the tree by just traversing it from left to right. And each time we hit a leaf node, we will submit a command to the GPU. So for instance, following this path, we emit the command that you can see on the right side. So fill the circle in yellow, and XF0 is the transformation that we computed by following the path. In this case, it's the identity transformation. Here we want to fill this, one of the eye. So we have some transformation which positions the eye, scales the circle down, and paint it in black. Same for the other eye, and finally the smile with yet another transformation. So what this gives us is the following performance model. We have geometry, which can be arbitrarily complex. We have trees, and we have sharing. So assuming we properly make use of sharing, we should not recompute the same geometry many times. Other nodes have a fixed size, so they don't consume much space or time. And finally, traversal of the tree needs to visit all nodes, so it's linear. And rasterization cannot benefit of sharing, but because it's done on the GPU, you will have a massive parallelism. And finally, devil is in the level of detail, because since we are simplifying the geometry, it's possible that we might have to revisit some of the geometry many times, but you shouldn't care about that kind of detail. The conclusion is, in the current state, we have a versatile vector graphics renderer. It has the declarative vector API that we wanted. We paid a lot of attention to performance and portability, and I can still understand the code base. So it's 3,000 lines of code, 1,000 lines for the API that is exposed to the user, 1,000 lines for the actual job of rasterizing, and 1,000 lines for interfacing with the operating system. So it's a rather small code base. And in the future, I would like to add a video game rendering. So basically it means giving up some attention to quality, but having more features and a faster rendering path that makes use of more hardware features. Yes, there is always some cleanup to do and performance to tweak. And finally, once we have these first pieces, we would like to build a full-featured graphics stack on top of that, so including event handling, user interface rendering, and so on. I would like to thank Pierre Chambard, Sébastien Mondet. So Sébastien, who did a talk a bit earlier, used this API to render the graphics, the GUI of its application. And he was very helpful and gave some feedback on the API. Jordan Walk also took time to explain some potential use cases, how to make it more usable, and yeah, many useful details. And finally, thanks to Mikko Mononen. So I don't know this guy, but he published some code for doing rendering on GitHub. It's a C library that is not functional at all, but which was a very good inspiration for understanding how to optimize for a GPU. And one last thing, so this presentation was not made with PowerPoint and so on. It's just pure OCaml that is being rendered with the wall library. And to write a presentation without a tool is very painful, so I designed it so that I can do live programming to use a slide. Thank you.
Okay, so we have time for some questions. Yes?
Your API looks a lot like VG. Can you
Yes.
comment on the differences?
So I did not invent the declarative model for rendering vector graphics. The work was started more than 10 years ago by Conal Elliott, and then Anthony Courtney in his PhD. And then Daniel Beasley reused this work to implement a more general declarative model, which is VG. There are various reasons why I don't use VG. Basically, I only expose the features that are easy to map to hardware. So if you want to use VG, what can be done is define a VG renderer that outputs the primitive understood by Bour.
And it will fail on the parts that are too hard.
Obviously.
Okay.
So you can consider this as a lower level. It's not that I didn't want to use VG, it's that VG is much higher in the stack than this. Basically, you don't commit to anything that you cannot do efficiently on the GPU by using this API. And
Yes, yes?
Well, I don't know much about graphics, but I've heard a lot about Vulkan as a potential successor to OpenGL. So you have things to say about that?
yeah, basically you can think of OpenGL versions, and Vulkans are some requirements on the underlying hardware. Like OpenGL or Vulkan are just an API to access this hardware, and because we target OpenGL ES, it means that we use a very small subset of what Vulkan can offer. If necessary, we can write a Vulkan backend. But as it is, we just target the less demanding API.
So I have a question. It's a kind of silly question, but so you mentioned that it's made for it's designed for user interfacing. But what you've shown us is the slides, which is one user interface. But you have other examples that look more like traditional user interfaces. So maybe Sebastian's code or what you have been playing with.
So this example was it's a bit big. I translated the example from Mikko Mononen, the guy I mentioned. This is the test he used for his NanoVG renderer, and this is the OCaml version. So you can see the performance in the background. It's not bad, roughly 7 millisecond per frame. And if you run this into a profiler, you see that all the jitterness comes from the Intel driver and not the OCaml GC. So the OCaml GC is, mostly transparent.
But, so does this demos support like input events, or is it something that is orthogonal and you haven't worked on?
Yes, it's orthogonal. As I said, I don't care about the windowing system here. I just assume there is a surface I can render to, and we will have to build other tools to interface all of this.
Yes?
I'm sure there's now a pattern to my questions, but have you actually tried this on JSOO or VocalScript or anything? Have you used this for WebGL yet?
Not
Or
yet.
just that's in theory?
Not yet. So there is one file that needs to be re-implemented to target another backend, and I just worked on the minimum. Like I make some assumptions which are true on Linux and macOS, and I didn't explore other systems, but they are not fundamental limitations.
Yeah.
So it's going to be a sort of difficult question, I guess. You don't use a toolkit since you want to write your own UI, so the goal is not to use a toolkit. But toolkit provides lots of things, in particular regarding accessibility and things like that. And I guess you're not going to rewrite those things. Do you think it's really a good idea to write a UI without a toolkit?
We write a UI without?
Without a toolkit, so GTK or
Oh
something like
yes,
that.
I spent a few years working on binding toolkits, using toolkits, and I think it's a really bad idea to use that kind of stuff. However, accessibility is a good thing, and there are low-level abstractions to talk about accessibility. So you can write in almost platform-independent way, basic description. So when you build this tree of abstract components, of abstract shapes, you could associate accessibility levels to each node. That's one way to express that.
If I can leak some information, Frédéric has been working on a Qt binding for a while, and we've been trying to convince him to talk about it. So maybe next time.
Maybe
Yes,
next time.
Anil, a short question.
I was wondering about text layout because for building CLI applications, it's really nice to have some graphics, but a lot of text. So do you have any kind of text rendering things, a bit like tech or something, that would help lay out large bodies of text?
Like tech.
Do the layout algorithms a bit like tech?
Yes, yes. The presentation was written with Bour, so all the text in the presentation was laid by this low-level library. There is just no nice high-level interface to it yet. There are many use cases, and I was tailoring for a specific one, so it's definitely possible to implement that. Also, the library cares only about rendering and not about layout, so you can plug a higher-level layout library to that.
Thank you.
Thank you.